Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, course schedule from LeetCode. This problem is great for learning cycle reduction graph. We'll explore DFS with cycle reduction. Let's break down the problem step by step and understand how to solve it. So sit back, relax, and let's dive in. So before we dive in, I want you to understand that this problem is asked in top product-based companies like Amazon, Apple, Google, Facebook, Goldman Sachs, Microsoft, and all. So yeah, now let's focus on the problem statement. So the problem statement is the total of num courses you have to take, labeled from 0 to num courses minus 1. You're given an array prefix where prefix of I is AIBI. So basically the prefix is a list of lists, okay? So in this inner list, we have only two elements, A and B, okay? This indicates that you must take course B first if you want to take course A. So basically here course A depends on course B. That means firstly course B has to be completed if you want to take course A, okay? For example, the page 01 indicates that to take course 0, you have to take course 1. So basically this course is dependent on this course. So first we have to complete this course and then only we have to come back to this one, okay? So return true if you can finish all courses, otherwise return false. Okay, so basically in which cases we can't complete all courses, you might have guessed it, right? If there is circular dependency. So basically if A depends on B and B depends on A, we can't take either of them, okay? In that case, we have to return false. So let's look into examples which would give you more idea. So in example 1, we have num courses 2. So prefix is 1, 0. So the output is true because here, if you see properly, what is the actual thing here? So if you want to take course 1, you have to take course 0, and it's very straightforward, right? You can complete course 0 and come back to course 1. There is no other dependency. So we output true. So the expression is also same. So the total number of two courses to take. To take course 1, you should have finished course 0. So it is possible, okay? And example 2. So here num course is equals to 2. The prefix is equals to 1001. So here if you observe, 1 depends on 0 to be completed. And here 0 depends on 1 to be completed. So basically this is circular dependency, right? So let me just put this in form of a graph. So this is our second example. So wherein we have 1 depends on 0 and 0 depends on 1. In terms of graph, if A depends on B, there would be a directed edge from B to A because B have to be completed before A, okay? So in this case, when 1 depends on 0, 0 has to be completed before 1. So that's why we have a directed edge from 0 to 1. In this case, 0 depends on 1. So 1 has to be completed before 0. So we have a directed edge from 1 to 0. Okay. So now if you see this is circular dependency, in this case, we definitely can't finish two courses. So that's why we have written false. So that's the same explanation that I've given here. The total number of two courses to take course 1, you should have finished course 0. And to take course 0, you should also have finished course 1. So it is impossible. Okay. And coming back to first example, this also could be represented in terms of graph as a directed edge from 0 to 1 because 1 depends on 0. That means 0 has to be finished before we take 1. Okay. So that's the idea, guys. So you got it right. The problem statement is very simple. We just need to represent the given prefix in terms of graph, and then we have to find if there is circular dependency. Here in this case there is no circular dependency, so we can finish all courses. So in this case we have circular dependency, so we can't finish all the courses. So here we have to return false. So if circle is written in graph, we have to return false. That's the main idea, okay? So what are the constraints here? Num courses is in the inclusion range of 1 to 2000. Okay, so total number of courses would be inclusion range of 1 to 2000. And prefix dot length is the inclusion range of 0 to 5000. So here prefix is there, right? This is basically a list of lists. So this list length is in the inclusion range of 0 to 5000. And prefix of I dot length, that is inner list in this list, okay? That has length 2. We see in here, right? The here and here, okay? And here also we saw, is just an example they give. And then here A, B are in the inclusion range of 0 to num courses minus 1. So why I said num courses minus 1? Because it is less than num courses. That is A and B would be always in the inclusion range of 0 to num courses minus 1. Okay. All the prefixes of I are unique. So we don't need to care of duplicates. Okay. So that's the idea, guys. It's very simple. And the main catch here is A and B are in the inclusion range of 0 to num courses minus 1. So here the nodes, whatever they give, could be in the range of 0 to num courses minus 1 because A and B are the nodes, right? If you consider any prefix. So here if we consider when num courses is 2, we have the nodes in the range of 0 to 1. And if num courses is 3, we have the nodes in the range of 0, 1, 2. Okay. So that's the idea. So it starts from 0 and goes till num courses minus 1. They are the nodes we have. Okay. So this is the boilerplate code given. So wherein we have a can finish method which takes num courses, which is an integer, and precise, which is a list of integers. Okay, and this returns a boolean. Basically, this boolean represents if we can finish all courses. So we had written true if we can finish, else we had written false. Okay. Now let's look into approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So now let's look into the approach, which is a depth first search with cycle detection. So what is the intuition here? Using DFS, we can detect cycles in the course dependency graph. If we encounter a package that is a node that's already being visited, the graph contains a cycle and it's impossible to complete all courses. So it's very simple, guys. We just need to put this precise in terms of graph, and then we have to find the cycle in the graph using the DFS. Okay. So now let me just take another two examples that would give you more idea. So here, if you have precise given as 1, 0, 2, 0, 3, 1, 3, 2. Okay, and then we formed a graph here. So if you see, so here 1 depends on 0, so there is a direction from 0 to 1. So we have 0 to 1. Okay, and next we have a direction from 0 to 2. And next we have direction from 1 to 3. Okay, and next we have direction from 2 to 3. So that's what the graph we have. And next thing, how do we represent this graph in our code? We can represent it in either adjacency list or adjacency matrix. So now we are going with the adjacency list because this is the optimal way. Adjacency matrix is sparse, that means like it takes extra space, but this is a more optimal space. Okay, so you can Google up the representations if you have any doubt in that. So now let's see how do we represent this in terms of adjacency list. So here we have nodes from 0 to 3. So that's why we are writing like 0, 1, 2, 3. These are the nodes we have. Okay, and each nodes we have the connection, right? So for that connections, we have to put it in a list. Okay, so if you take one, what is the connection? It has 3. Okay, so the directed edge I'm talking about. So this directed edge is the connection we have. These are neighbors. Okay, we can say it as an edge as well. So 1, 2, 3. Okay, so and from 2 we have only directed edge to 3. So that's why we put only 3 as a neighbor to 2. And for 3 there is no directed edge coming out. So that's why it's an empty list. And from 0 we have the 2 directed edge coming out to 1 and 2. That's why we put 1 and 2. This is the adjacency list representation. Okay, it's very simple. And then we have the another precise here. Okay, so this is circular case. So here there should be a directed edge from 0 to 1, and then directed edge from 1 to 2. So that's what we have, and then from 2 to 0. Okay, so here you see this is circle, and there should be directed edge from 2 to 3. Okay, so this graph would give you more idea while we see the algorithm. Okay, so here we have cycle from 0, 1, 2, 0. Okay, so now let's look into algorithm and come back here. So now let's look into algorithm here. So what is step 1? Represent the course dependencies as an adjacency list. So this is what we just discussed. Okay, so adjacency list is nothing but a form of graph in code. Okay, so here step 2, maintain a visited list to track the state of each node. So we have 3 states defined for the nodes. 0, that means node is not visited. 1, that is node being visited. So currently it's in the DF stack. And then 2, which means node fully visited. That is all of its neighbors should explore. Okay, so we have the 3 states. Okay, so in step 3, perform DFS for each course. If a node being visited is revisited, that is, it is in the state 1. Don't worry about this. I'll show a dry run which would give you more idea. And then we mark nodes as fully visited after all neighbors should explore. So in step 4, if no cycle is found in DFS, all courses can be completed. So that's the idea, right? So basically there is no cycle. We see that we can complete all courses. Okay. So now let's look in the dry run of this algorithm. So firstly, we have a visited list state. I just named it as VS. So this maintains the state. So this list size should be same as number of nodes. So here we access the state of the each node by using the index. So that's because our indexes are in the range of 0 to num courses minus 1, right? So that's why we just map this index to the node state we have. Okay, so that's why whatever nodes we have, that many entries should be there in the VS. That is visited list here. It's not set. Okay, visited list. I just kept it as VS. This shortcut. Okay, so as we discussed, we'll be having 3 states for a given node. So firstly, we'll start with 0 for all nodes because all nodes are not visited in first, and then we start going from 0 here. Let's say we go from 0. So in DFS, the basic theme is we have to visit neighbors aggressively. So if we take 0, we have to visit 1, and then from 1 we have to visit its neighbors 3, and then we come back to 1, then we see if there are any neighbors left for 1. If no neighbors left, we go back to 0, and then we explore the neighbors of 0, which is true. Okay, it's that way. Okay, so this is how DFS works. And then we discussed about the states, right? So firstly, as we visit course 0, we maintain the state here, right? So for that case, we had to keep 1 here, which is just the state representation of that particular course, and then we go to 1. So basically we visit 1, right? So while we visit 1, we had to make changes here because we change the state, right? So that's why we keep it 1. And from 1 we visit node 3, so we had to update the state here. So let's update the state. Notice here I'm just changing at the particular index. If the course 3, I'm changing at the third index. Okay, and now from 3 there are no neighbors left, so we go back to 1. So as we backtrack to 1, that means we completely visited node 3. So that's why we had to put the state of node 3 as 2. Okay, since it's completely visited, because there's no other neighbors left from 3. Okay, and now from 1 we go back to 0 because there is no other neighbors left from 1. Okay, so that's why we had to change the state of 1 to 2. So here we just change the state. So from 0, now we have another neighbor left, which is 2. So as we visit 2, we have to update the state. So here for the second index, I'm just updating the state to 1 because it is being visited. So from 2 we visit 3 because 3 is a neighbor. But here 3 we see, right, it's already visited, so it's not a cycle. So we saw, right, like if a node is being visited, but if it is in state 1, there is a cycle. But here there is no cycle because it is already visited, completely visited. This is completely different traversal. Okay, and you get more idea when we see this case. Okay, so here we visit 3, and then which is already visited, so we just come back from that because we don't need to visit it. There is no cycle, and then we backtrack to 2, and then from 2 there is no other neighbors left, so we backtrack to 0, and when we backtrack to 0, we have to update the state of 2. So here the state of 2 becomes what? It is 2 now. Basically we visited all neighbors, right? So that's why it's 2. Okay, so now we come back to 0, and then we mark it as 2 because all of the neighbors were visited. Okay, so now let me just put this. So now we saw a case of acyclic graph. So now let's look into this cyclic graph. This would give you the proper understanding of the algorithm. So here also we initialize our visitor list to all 0. Okay, and next we start visiting from our node 0. Okay, so for that case, as we visit the node 0, we have to mark the state accordingly. So here let me just update 1 for 0. So basically this is the state, right? So that's why. And next we go to course 1, and now we have to update the state for the course 1. Okay, let me just update this. So I'll just keep it as 1 here for the state. Okay. So from 1 we visiting course 2. Okay, so now we have to update our course 2 state as well. See, I'm changing this particular index. Okay, so let me just update this. Okay, so from 2 we have the 2 edges, so we can visit course 3 or course 0. Okay, so now let's explore course 3. Okay, so as we explore course 3, what we have to do, we have to update the state here. Okay, so let me just update the state here. So from 3 we backtrack to 2 because there is no neighbors left from 3. So now what we had to do, we had to update our course 3 state to 2. Basically we explored all of its neighbors, right? So nothing left to explore. So that's why we update our state to 2. So and now we backtrack to 2. And now after this we have to explore our node 0. So if you see, when we go to node 0, the state of node 0 is 1. That means that we are still in the process of visiting all nodes from node 0, but we come back to node 0. So there's a cycle. So if see, right, this is the same step mentioned in our algorithm. So here in step 3 we have if a node being visited is revisited, that is in state 1, there's a cycle. So that's what we have here, right? The same thing we got. So here we visited the course 0 again, and the state is 1. That means there's a cycle. So that's how we get a cycle. So basically here if we revisit a node again and the state of the node is 1, that means there's a cycle. So that's the key catch here. Okay, so now let's screen the code. So firstly we have to represent this pictures in terms of graph, and then we have to find the cycle in the graph. So if there's a cycle in the graph, we can happily return false because there is no way to complete all the courses. And then if there is no cycle, we can return true. Okay, we have to complete all courses then. So for that matter, firstly we are building the adjacency list. So adjacency list is nothing but the dictionary in Python. So that's why we're using the dictionary combination here. So what we are doing, I:empty list for I in range of num courses. So this would form a dictionary like this. So here the key would be the node value, which is 0 and 1, and this the values of this key would be the empty list. Okay, and next what we're doing, so for course and prerequisites, so basically this is our prerequisites list, right? So in this there is another list which is course and prerequisites. So that's what I'm grabbing here, and then what I'm doing, adjacency list of prerequisites dot append course. So why I'm doing that? So if we represent this in terms of graph, there is a directed edge from 0 to 1 and there is a directed edge from 1 to 0. Okay, this directed edge means that 1 is a neighbor of 0. Okay, so here if 0 is what the prerequisites, so for prerequisites our 1 is a neighbor, so that's what we are doing here. So adjacency list of prerequisites, we're grabbing the prerequisites and then we're appending that course. Okay, so we're grabbing 0 and we're appending the course, which is 1. Okay, and next we're grabbing 1, we're appending 0. Okay, so that's the idea, guys. It's very simple. And next we initialize our visited list. So we're just initializing the visited list to all zeros here. So what we are doing is a shortcut format here. So if we multiply 0 with number of courses, if number of courses is 2, we'd get a list of lengths 2 initialized with all zeros. Okay, and next what we're doing, we perform DFS for each course. So for DFS we should have one function defined, right? So that's why we define the function here. So here we define the hash cycle function which takes the course. This is the recursive notation. That's why we define the base cases. If there's no base case for the recursion, then it would keep on calling itself and it would give us a recursion depth extender. So for that reason, we should define the base case. Okay, so our function main aim is to detect the cycle. So if we can say that there's cycle or there's no cycle, that's the base case for us. Okay, so here firstly we're checking the visited of course. That means the state of this course is 1. That means there's a cycle, right? Because we visited this course again while all of its neighbors are not yet visited. Okay, so that's why we return true. And next, if the course state is true, that means that we already visited this node completely and we come back to this node. So there is no cycle. We saw this on a dry run. Okay, so these two are the base cases. And next we go to the actual processing. Okay, and next what we're doing, we're just marking the course state as 1 because we visited this node, so that's why we had to change the state to 1. And next we have to expect all neighbors of this node. So for neighbor in adjacency list of course, so for this course we have to expect all neighbors. So if hash cycle of neighbor, that means we just recursively calling this method here. So if this returns true, we have to return true, right? That's why we just return true. And next, after visiting all neighbors, we just mark the node as fully visited. That's why we change the state to 2 here. Okay, so at the end, if we didn't return true here, that means there is no cycle, so that's why we return false. So this is our hash cycle method, and here for course in range nums courses, we're just calling our hash cycle method. Okay, if this returns true, that means there's a cycle, so that's why we have to return false. Okay, and next, if we don't return false here, that means there is no cycle, so that's why we have to return true here. Okay, so now let's run the complexities. The time complexity is O of v plus c, where v is the number of vertices and e is the number of edges. Because here each vertex and edge is plus 1, it remains O of v plus c. The space complexity is O of v plus c, and this is for the adjacency list and the recursion stack. So basically, this adjacency list has a space complexity of O of v plus c because we have to represent the vertices and edges, and this recursion stack would at most hold the v vertices. So that's why it's O of v. So actually this would be O of v plus c plus O of v, but in effective it is O of v plus c because O of v plus c is greater than O of v. That's why we consider this effective space complexity, so it is O of v plus c. So I got the code ready here. Let me try running this. So this accepts solution of the two cases. Let me try summing this. So this accepts solution for all the test cases and beats almost 91% of this. Cool, right? And this should wrap and solve the course schedule using DFS approach. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.